Hello, everyone. Welcome back, potentially, or welcome if it's your first time. My name is Michael. I am a math major at Carnegie Mellon, and I'm here to help you do your first proof. For whatever reason you are getting into proofs, maybe you're a first year math major. This is your first class. Maybe you're just trying to dabble in math proofs just because it's something that's interesting to you, or maybe it's just a prereq and you're trying to go into a different round, like computer science or something. But this is something you have to get done anyway, um, and you're just starting proofs for the first time. And proofs are hard. Proofs are very hard. It's a different way of thinking than and problem solving than you've probably ever done before, because it's much more rigorous. The language and the level of, I guess, rigor that you need to put into your proofs are much higher than your everyday language, or probably the arguments that you've made thus far, because they need to be proofs that can be universally accepted, or are so strict and rigid that it's impossible for other people to poke holes in them. And that's just the world of formal mathematics and proofs as a whole. And it's likely something you've never done before, and I'm here to assist you in that process and give you some extra tools to help you focus on the content, as opposed to, okay, well, how do I actually write a proof? So yeah, let's jump right in. One of the first things we're going to talk about, when you have a question or a proof that you've never seen before, the first thing you want to do is intuitively understand what you're being asked. You need to understand the question. So maybe you're new to formal math and you've never seen all this notation before, and they give you this problem that's just symbols on symbols. So trying to prove something like that makes absolutely no sense. And we have no idea where to even go with the question until maybe we turn it into English. We take that logic and make it into a language that we can actually understand and then reason about. Or maybe it's this lengthy word problem with lots of different nuances, and it could be much easier to approach if you turn it into logic. We're going to talk about later some of the logic really dictates how you do a proof. So if you just interpret the logic correctly, then you can just take steps based on that. One example that we'll kind of just quickly go through, and we have another one as well. Prove x squared minus y squared is divisible by 2 if x and y are even. I'm actually going to change this to be is even. If x and y are even. So this is just words on a page. How can we turn this into logic? Well, we want to take this and go, okay, we are going to reference this in the future, but we want to get something in the form of like P implies Q, some type of logic. So if we have to assume something first and then we want to show it, we're actually going to have this be our P and then this be our Q. So if this is P, this is our Q. Don't worry too much about this. This is just how we can show something in logical notation. So then we can say x squared minus y squared even. You could even say something like 2 divides x and 2 divides y implies 2 divides x squared minus y squared. And how is this helpful? Well, if we think about x and y being even numbers, then x squared and y squared are both even numbers. And if we know that an even minus an even is equal to an even, then we know the difference of two even numbers is also even. So we just did some reasoning that might not have been as clear as before if we hadn't put it into a format that makes more sense. And we're going to talk about how this approach makes more sense in the next kind of topic. But here's a problem that likely, if you're new to proofs, whoa, what am I even looking at? It's a bunch of notations, a bunch of symbols. How do I break this down? How do I actually understand what's going on? Because if I just look at this, I don't know what I'm doing. So maybe take a second, try and read through it. But the first thing we're going to do is try and get some conceptual understanding. So for all x and y and r, there exists a z in the rationals such that the minimum of x and y is less than z, which is also less than the maximum of x and y, or x is equal to y. So what is this actually saying? Maybe we just say, okay, well, let's just say x is smaller than y. X is less than y. Just because. And now we can think of this as a number line. Whenever we see kind of this inequality type of thing, we can think of this as being numbers on a number line. So maybe this is our x and y, and we want to say this is our z right here. We want to show that whatever x and y are, there's some z that can be in the middle of them. Or if x and y aren't equal, or if x and y are equal, then they would actually be like this, and then there's no number in between them. And of course there's no z that we could use that's both less than or greater than the min and max of them both. So this kind of gave us a little bit more intuition on how we would approach something like that. Now, the actual math we'd have to do is, well, how do we figure out that z that satisfies this equation? And that's part of your actual proof. But now we actually know what we'd want to do. We'd want to be able to determine a value for z that would make this true. So some z in between x and y, and that's something that's much more easy to understand than all of this logic right here. That's likely more confusing. Moving on, now we're going to talk about your next step after you understand the question. So once you understand what you're actually being asked and what you're being asked to prove, now you can identify the actual proof method that matches what you're being asked to prove. So some of these are going to work better than others, but just looking at them first, we're going to have a direct, a contrapositive, and a contradiction. These are some big ways of proofs that you should familiarize yourself with. But the main idea is we always are trying to prove this big statement here, this P implies Q. Almost everything is going to fall into some type of P implies Q. And we could just approach this directly. And how do we do that? We assume P and we show Q. So this is the same format regardless of what P is. Maybe P is equal to some X or Y and Z, whatever it is. If this is meant to imply something else here, whatever it is, we're just going to assume all of this P and then show all of this Q based on that P. And then that's the exact same format for every direct proof regardless of what P and Q are. But this gives you some overall structure into how your proof should look if you're going to do a direct proof. Very similarly, we have contrapositive, which kind of takes the opposite approach of P implies Q. So when we're saying P implies Q, we're looking at kind of like half of what Q could be. Maybe we say the opposite of what Q is would then imply that we couldn't have had P to start with. So if we're kind of looking at the other side of the coin here when we say contrapositive. So we're going to take not Q implies not P. So we swapped our order for Q to P, and then we negated both of them. But now we've got something in that direct format. We just have it's just a slightly more complicated expression with not Q and not P. But we could think of these as the P and Q that we put into our original direct proof, and then we know how to approach a direct proof, and we can just do it that way. So this would be essentially our new P, and this would be our new Q. So we're going to assume not Q and then show P. And it's the same exact structure, except maybe it's easier to reason through the not Q and not P than it is the P and Q. So whatever proof approach you take will depend on the problem. But this is some kind of overall structure to give you. And then a contradiction is when we assume P and not Q. So instead of taking our P implies Q directly, we're going to say we have P is true, but then we don't have Q is true, which Q should be true. So in this case, we have two things that should contradict each other, and we should eventually reach, if we use logical reasoning, something that should never be true. So maybe this is something along the lines of like a 1 equals 0, or a number being even and odd at the same time. These are things that could never happen. And if we take our original premise of P and not Q, and then eventually derive a contradiction, then we know our P and not Q was false. And that's something we incorrectly assumed, which would mean that P and Q are true. But yeah, so let's kind of look at an example of that. One way we could turn this into some notation is if A divides B and B divides C, prove A divides C. So if we have A divides B and B divides C, we want to show that this implies A divides C. Now, we have this format of, let me use a different color. We have this format of P implies Q. So what are we going to do? We're going to do exactly what it says here. We're going to assume P and show Q. So we'd assume A divides B and B divides C, and then we want to show A divides C. And then the hard part is actually showing A divides C, but that's when you can focus on the actual math behind the problem and not the, okay, where do I even start? So you know where to start now. That's the main goal of this, is helping give you some direction on where do I start, and then the actual problem solving can be applied to the math. Going at another problem, this, if we have if n squared is not even, then n is not even. We already have these negatives right here. It might be better to get this into a not a negative type of thing. So we have this n squared is not even implies n is not even. But reasoning about n squared can be relatively hard, because we would have to look at, okay, well, what are the factors of n squared going to be? And then try and reason about something like a level lower. And maybe it doesn't. Maybe it has other factors. So maybe this isn't the best way to do it. But reasoning about n, going from n to n squared, is much easier than going from n squared to n. Because squaring something is less complicated than taking the square root. So we have currently a P implies Q. So we could use our contrapositive of not P, not Q implies not P. So then we have n is even implies n squared is even. And then this is so much more straightforward than what we had before. And again, this isn't a crazy example, but it's something that can hopefully make more sense. Because like squaring an even number, if we think of it as being 2k, then n squared is 4k squared. And this has a factor of 2 in it, and we're already done. It's very straightforward. But it accomplishes the exact same job. And then I'm going to skip over this one. I'm going to say, then we have a couple extra helpful tools that'll make our proof life easier. One of them is casework. So we have to do something where if we're trying to prove something for this big group or this big collection of things, if I draw this kind of like circle here, Um, Maybe proving all of them at the same time is a little rough, but if I split it up into pieces, then maybe proving this one individually and this one individually will make our lives that much easier, and then we can make an overall claim about the entire thing if they all reach the same conclusion. So some common examples are, if we want to prove something for every number, maybe we split it up into even and odd, or maybe negative, zero, and positive. And then these are just examples, but the idea is you can just partition your group into different into partitions, and then make logical reasoning about each individual group. Another tool that's super helpful is using a counterexample. So this can be very helpful when you're trying to derive a contradiction. And it can also be very helpful if you don't know if a statement is true or false. You won't always be given a question that's prove that this statement is true or prove that this is false. It might be something where it's like, prove this is true, or give a counterexample for why this is false, or something along those lines. So thinking of those specific counterexamples where maybe there's a scenario where you divide by zero, or where you take the square root of a negative number. There are these special cases that can make these general statements not true, because they're saying it works for everything, but you've got this one number that it doesn't work for. So these counterexamples can be very helpful in making your proof life easy. And then the hard part is just recognizing which number is going to be the best type of thing, or which choice will do the job correctly. If we go to the final step, or the final kind of tool in this toolkit for you, is letting the question really guide you, and not trying to jump in too quickly, and just learning the patterns of each symbol, of each proof method, because a lot of math is just pattern recognition. If you see the same proof in different forms a lot, then knowing how to attack that original proof can be so helpful in a general manner, because then you can utilize it and make it, in a sense, modular, and apply it to all these other different types of questions. So one example is we have this for all x and a. A very easy first step you can do in your proof is just consider some arbitrary element of a and let that be your x. And then you can reason about this x however it is, but it has to have the properties of anything in A. But then again, that first step of letting x be an A, it's almost guaranteed when you see something like for all x and A, ... So maybe there exists a y and b. The first thing you'll do is let x be an arbitrary element of A. And then likewise, if we have a there exists, then we do a choosing y to be some specific element of b. So instead of it being arbitrary, now we can make a specific choice. And this is often where you'll want to be clever, I tend to say. You want to cleverly choose your y to make your statement true. So if these are our quantifiers, then we're going to have some statement here. And the idea is we want to give ourselves values to work with, so then when it comes to proving the bulk, we already know what we're going to do. And this is just ways for you to lay out your proof without having to do any of the hard thinking yet. But the main difference between these two is that x has to be arbitrary and thus have any property of every element of A, whereas y can be very specific and doesn't need to be a representative of all of B, and can even be reflective of x in this case. So maybe y is like equal to negative x. And then because y is equal to negative x, they have some important property together. But we can choose y very specifically. And what you choose for y will vary on the question and is something you'll build with time. But these are ways to kind of generally approach when you see this type of notation in a problem. And then two other main examples would be subsets. If I have A as a subset of B, then we just say let X be in A and then show that X is also in B. If A is equal to B, where A and B are sets, then this is something called double containment. We just show A is a subset of B and B is a subset of A. And then finally, a by implication, if P, if and only if Q, so this is sometimes we write it as like a if and only if, we call this a by implication. The way we prove this would be P implies Q and Q implies P. So this would be an example of like a logical equivalence between the two. But these are all very general ways of approaching a specific problem type. Now, the idea is what your A and B are, or what your X and Y will be specifically, is going to change from problem to problem, but the same ideas are always there. And if you can apply those same ideas and then just tweak them to fit the context of the problem that you're in, it's going to make your life that much easier. And then you can just focus on the underlying math of that problem, as opposed to, okay, well, how do I prove something directly again? So hopefully this gave you some foundation